This is Dr. D. Govardhan, Professor Emeritus, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing bars of uniform and varying cross-section, numerical problems in mechanics of solids. The stresses in the bars of uniformly tapering sections. There are two types are there. We are considering the section which are having uniformly tapering sections. One is bars of uniformly tapering section, circular. The second one is uniformly tapering rectangular sections. Okay, in first case, stresses in the bars of uniformly tapering circular section. L, let P be the force P acting. Here it is tensile in nature. Let D1 is representing the larger diameter of the uniformly tapering circular section as shown in figure, and D2 is representing the diameter at the smaller end. Now consider small element of length dx of the bar at a distance of x from the bigger end as shown in figure. Here we are considering this is known as a small section now. It is at a distance of x from the bigger end as shown in figure now. First of all, let us determine what is the stresses that is acting on this elementary area. dx is representing its length at a distance of x. Now, first of all, we determine what is the area of this elementary area now. That is diameter required. Here d1 is representing the diameter at the bigger end, and d2 is representing the diameter at the smaller end of the tapering section. So dx is equal to, since it is uniformly tapering now, it can be written as d1 because the value is decreasing now, minus d1 by d2, that is here now d1 minus d1 minus d2, that is this length is nothing but decreasing for the length L, but we are considering at a distance of x, hence it can be written as like this now. So that is the diameter at a distance of x, as in this is nothing but dx, it is equal to d1 minus d2 by L into x now. Here it is equal to d1. Since d1 minus d2 divided by L, it is the constant now. Hence, I am taking it as k into x, which is equal to dx now. That dx is representing the diameter of the circular bar at a distance of x from the bigger end as shown in figure now. Then the cross-sectional area of the bar at this section is equal to, that is pi by 4 into d square. Pi by 4, d square is equal to d1 minus kx whole square now. Now stress is equal to the force by area, where P is representing the force that is acting on the body, which is in tensile in nature. Hence elongation of the bar is taking place, which is equal to P by area, that is P by Ax now, which is equal to P by area is equal to P divided by pi by 4 d1 minus kx whole square. This by 4 is there now, it comes to numerator. It can be written as the 4p into pi into d1 minus kx whole square. So strain is equal to, we can written as stress by strain is equal to Young's modulus. Here it can be written as now stress by strain E is equal to, that is Young's modulus is equal to stress divided by strain now. Here the strain at a distance of x is equal to, assume sigma x, it is equal to given, sigma x is representing the stress and epsilon x is representing the strain now. So strain is equal to, we can take it as strain is equal to sigma x divided by here x small s now, which is equal to sigma x divided by E now. Sigma already we have determined now, that is stress is equal to 4p into pi in 4p divided by pi into d1 minus kx whole square, which is equal to 4p divided by E, just we are taking additionally E into pi into d1 minus kx whole square. The elongation of the elementary bar, here epsilon is equal to stress is equal to strain is equal to, we can take it as a change in length by just the original length of the object here, which is equal to, this is the equation now, but I required the elongation within the small length dx, which is equal to, I can take it as now delta Lx is equal to epsilon x into L now, which is equal to epsilon x into L is equal to here dx, where dx is representing the length of the elementary area considered. Here it is equal to epsilon x into dx, which is equal to the strain is equal to stress divided by young small s, hence it is equal to sigma x divided by E now into dx now. From this relationship we got to 4p into, because the sigma x is equal to 4p divided by E into pi d1 minus kx whole square into dx. The total elongation produced in the tapering section is obtained by integrating the equations from the limits 0 to L, that is 0 to L sigma x divided by E now, which is equal to 0 to L 4p divided by E pi into d1 minus kx whole square into dx now. So it can be written as now 4p, it is a constant now, E by p also constant, the remaining values is there now, that is d1 minus kx whole square, it is there now. The integration of d1 minus kx whole square, integration 1 by d1 minus kx whole square is equal to, it is equal to d1 minus kx whole to the power of minus 1 divided by minus 1 into k into minus 1. So by using this relationship we got 4 pi divided by E pi k into 1 divided by d1 minus kx whole to the power of minus 1 now. So on applying the limits from 0 to L in that equation, the total elongation produced because of application of the force P is given by 4p into divided by E pi k into 1 by d1 minus kl minus of 1 by d1, that is applying the limits, upper limit from the limits 0 to L now. Okay, substitute the values of k in this equations we got, that is delta L is equal to 4pl, it is there now, divided by E pi d1 minus d2 into 1 by d2 minus 1 by d1 now. Simply it can be written as now 4 pi divided by E pi into d1 minus d2 divided by d1 minus d2 divided by d1 d2 now. This is nothing but we have taken here LCM now. From this relationship we got 4pl divided by E pi d1 d2 now. Finally, because just to get the cancel now. It can be written as now P into L divided by E pi d1 d2 divided by 4 now. Now this is the equations applicable for the determination of elongation produced in the tapering section of the bar now. If it is having uniform diameter, that is D1 is equal to D2, and substitute the values D1 is equal to D2 equal to D, assume it is the diameter of the bar, uniform bar. The finally we got to it is equal to 4pi divided by E into pi d square divided by 4. This is nothing but general equations earlier we used for the determination of elongation produced in the bar of uniform cross section. Okay, the problem based on uniformly tapering section. A circular array of bar 2 meters long uniformly tapers from 30 mm diameter to 20 mm diameter as shown in figure. Calculate the elongation of the rod under the axial force of 50 kilonewtons. Take the Young's modulus for the alloy as 140 gigapascal. So length of the bar is given 2 meters. 2 meters means just we are converting all the dimensions in terms of millimeters. Hence it should be multiplied by 10 to the power of 3. Hence this value is equal to this one. 32 into 10 to the power of 3 mm now. The diameter of the circular cross section at the bigger end, let it be D1, it is equal to 30 mm now. The diameter of the circular bar at the smaller end is given by D2, which is equal to 20 mm now. The modulus of velocity is equal to 140 gigapascal, which is equal to 140 into 10 to the power of 3 Newton per mm square now. The elongation of the rod is equal to, as per the previous derivation, we have 4PL divided by E into pi D1 D2 now, where E stands for the Young's modulus of the alloy, which is equal to 4 into the force which is acting on the rod is given by 50 kilonewtons, and so 50 into 10 to the power of 3 divided by E 140 into 10 to the power of 3 pi D1 D2. These are nothing but representing the diameter at the both ends, which is equal to 30 into 20 now. So finally we got this value which is equal to 1.52 mm. Here we are considering uniformly tapering rectangular section. This rectangular section, it may be in the form of rectangular, alloy the square. We have to determine the stresses produced within the bar now. Here the problem 2 we are taking an alloy bar of 1 meter length as a square section throughout, which tapers from one end of 10 mm by 10 mm to the other end of 20 mm by 20 mm. Find the change in its length due to an axial tensile load of 30 kilonewtons. Take E for the alloy as 120 gigapascal. Here the given data in the problem is the length of the bar is given, it is equal to 1 meter. We are converting all the dimensions into millimeters, which is equal to 1 into 10 to the power of 3 mm. The section at the smaller end equal to is equal to 10 mm by 10 mm is given now. The area is equal to 100 mm square now. The section at the bigger end, it is given 20 by 20. The area is equal to 20 by 20 is equal to 400 mm square now. The tensile load is equal to 30 kilonewtons, 30 into 10 to the power of 3 newtons. Modulus of velocity equal to 120 gigapascal, which is equal to 120 into 10 to the power of 3 Newton per mm square now. So this we are solving these problems by using the fundamentals. Here consider a square of square at a distance of x from the smaller end as shown in figure at a distance of x now. So here we are considering from this position now. Here it is representing small area which is equal to, here the length is given dx at a distance of x now. So which is equal to, since the area at this position, it is gradually just varying, increasing its values. Assume A is representing the area at the smaller end and B is representing area at the bigger end now. So according to this formula now, A plus B minus A divided by x into L now. It is similar to the previous derivation, A plus, because it's nothing but in the form of tapering it is going on now. Like this, at a distance of x we are taking now. Length is equal to dx. It is equal to A is given, here the B is given now, which is equal to A plus B minus A divided by L, but it is a distance of x, and this is the values now. So it can be written as now A plus B minus A into x divided by L now. In this one, B is representing the area at the bigger end now, and A is area at the smaller end. L is equal to the length of the taper section now, and considering at a distance of x now. So it can be written as B minus A, L is the constant for that particular section. Hence, we are taking it as K now. Simply it can be written as A plus K x now. Then the cross-sectional area of the bar at this section is equal to, here we can consider that A and B are the, here now, the sides. If you take area also, this we are having the same problem now. Here if I consider it is A now, and B is the side at the other end now. So area is given by A plus Kx whole square now. So the stress is equal to force by area P divided by A plus Kx whole square, and strain is equal to, we can take it as stress by Young's modulus, that is the stress divided by Young's modulus. So stress is equal to force by area, force divided by area is equal to A plus K whole square into divided by Young's modulus now. The total elongation produced in the tapering section because of application of the force is given by integrating the above equation now, this equation from the limits 0 to L now. That is 0 to L, P by E into A plus Kx whole square into dx now. So total elongation produced, which is equal to P by E now, is a constant we have taken out. The remaining values A plus Kx whole square is there. It is when I am taking just at the numerator, minus 2 it is there. But when we are doing integrations, n plus 1 divided by, here x square integration is equal to x2 plus 1 divided by 2 plus 1. By using this equation, so here we will get A plus Kx whole power of minus 1 divided by minus 1. And integration of here Kx is there, it is a K. We can take it in the denominator now. So this value is equal to minus of P by Ek into 1 divided by A plus Kx whole power of minus 1 now. So applying the limits on these equations, we got delta L is equal to, we got it now, minus P divided by Ek, it is a constant now, 1 by A plus K minus 1 by A. So substitute the values of K in the equation now, we got delta L is equal to minus P by L divided by E into B minus A divided by 1 by B minus 1 by A now. So here B by A is nothing but, here LCM is nothing but A cross B now. This value is equal to minus of PL divided by E minus into B minus A. Here 1 by B, 1 by A is there now. Here AB is representing the LCM, which is equal to again A minus B now. So from this equation we got it is equal to PL divided by E into BA, where B into A is representing the Here now, the product of the side of the square at bigger end as well as the smaller end now. So if it is representing the thickness now, it is there now, we can take it as this value is equal to P into L divided by E into A now. Now substitute the values in this equation according to our problem now. Yes, we have delta L is equal to 30 into, that is the force, into 1 into 10 to the power of 3 L divided by E is equal to 120 into 10 to the power of 3 into A is equal to 20 into 10 now. This is nothing but both the sides. Finally, we got this answer is equal to 1.25 mm. Okay, in the previous problems, that is on both the ends, it is in the form of square cross section. So we have taken that as a product of the sides of on both the ends, B into A taken now. But in these problems, here the thickness remains constant, but the depth is now gradually varying from bigger end to smaller end now. So we are considering this type of problem here now. A steel of plate of 20 mm thickness tapers uniformly from 100 mm to 50 mm in the length of 400 mm. What is the elongation of the plate if an axial force of 80 kilonewtons acts on it? Take E is equal to 200 gigapascal. A steel of plate of 20 mm thickness tapers uniformly from 100 mm to 50 mm. That is the thickness is 20 mm, it remains constant on both the sides now. Here, the side length is given at a bigger end it is equal to 100 mm, that is reduced to 50 mm as shown in figure now. It is gradually varying from the bigger end to smaller end uniformly. Okay, the given data in the problem is a steel of plate of 20 mm thickness tapers uniformly from 100 mm to 50 mm in a length of 400 mm. Here, thickness is given 20 mm. The width at A is equal to 100 mm. Width at B is equal to, that is 50 mm. Assume this is the end A and end B as shown in figure now. The length of the rod is equal to 400 mm. Axial force is equal to 8 kilonewtons. Hence it is equal to 80 into 10 to the power of 3 newtons. Modulus of velocity is equal to 200 gigapascal. It is equal to 200 into 10 to the power of 3 Newton per mm square now. The total elongation of the plate may be found out by using the relations. Here it is given by delta L is equal to P into L divided by Et into A minus B. It is multiplied by log A into A by B now. So the way A and B is representing the width at bigger end and the smaller end. If you multiply by T on both sides now, like this is nothing but A into T is treated as the area of the bigger end, B into T is treated as the bigger end, smaller end. Here also we can do the same thing now. If you go just inside A into T and B into T now. So the modified equation it can be written as now B into L divided by E into A minus B multiplied by log E A by B now, where A, capital A and capital B is representing the area of the cross section at the ends A and B respectively, which is equal to, you can take it as log E is equal to, we can take 2.3 into, we can log base 10, we can take it now, which is equal to P into L E T, it can be written as now A minus B divided by log 10 into A by B now. So on multiplication of 2 by 3, P is equal to 80 into 10 to the power of 3 and L is equal to, length of the bar is equal to 400 mm, it is given, and E is equal to divided by 200 into 10 to the power of 3, and T is equal to 20 mm. A is equal to 100 minus here B 50 into log base 10, 100 divided by 50 as shown in figure. And doing this calculations, we got this value is equal to 0.1 mm, 0.11 mm now. Okay, this is the elongation produced in the bar, which is having uniform thickness, and the breadth is varying from 100 mm to 50 mm as shown in figure now. Okay, similar problem one more is a rectangular bar made up of steel plate is 202.8 mm long and 50 mm thick. The rod is subjected to an axial load of 40 kilonewtons. The width of the rod varies from 75 mm at one end to 30 mm at the other end. What is the elongation of the rod if E is equal to 200 gigapascal? The given that in the problem is the length of the bar is equal to is given a 2.8 meter is given, which is equal to 2800 mm. Plate thickness is given now 15 mm. Width at A is equal to 75 mm. Width at B is equal to 30 mm. The axial force P is equal to 40 kilonewtons. That means 40 into 10 to the power of 3 newtons. Modulus of velocity is equal to 200 gigapascal, 200 into 10 to the power of 3 Newton per mm square now. Let delta L be the representing the elongation of the rod because of tensile force P, which is given by P into L divided by E into T into A minus B into log A by B now. Okay, by using these relations now, when log when it is converted into base 10 now, it can be written as 2.3 into P by P into L divided by E into T A minus B into log 10 A by B now, which is equal to 2.3. P is equal to 40. Since it is kilonewton is given, 10 to the power of 3, and L is equal to 2.8 meters is given, 2.8 into 10 to the power of 3 divided by here E 200 gigapascal, 200 into 10 to the power of 3 Newton per mm square. Here T is equal to, that is thickness 15 mm is given, A minus B 75 minus 30 into log base 10 75 divided by 30 now. This on doing this calculation, so finally we got the value is equal to 0.76. Okay, stresses in the bars of composite structures now. A bar made up of two or more different materials joined together at the both the ends. That is here now, one is representing one materials and second is nothing but representing another materials. They are joined together here now at one position now, and again joined at the bottom position. After that, they are subjected to same load as shown in figure. This type of bars are known as the composite bars. Here in composite bars, according to the geometrical constructions, it will give us the extension or the contractions of the bar depending upon the load is always equal in both the cases now. In both the bars, when it is subjected to the load, it may be the tensile or the compresses. The elongations or the contractions is equal in both the bars now. The total external load, that is P, what is acting on it, it is shared by two bars 1 and 2 as shown in figure now. So the load bearing this in each bar is equal to the if P1 and P2 is representing the load shared by the two bars, then the total load is obtained is equal to the sum of the load shared by each bar now. That is, here if it is representing P1 is representing the P1, it is the load, and P2, the total load P is equal to, it can be written as P1 plus P2 now. That means when it is subjected to some external forces, it is shared just within the load such that the sum of the load shared by each bar is equal to the total bar, and the elongation produced in each bar is always equal now. Here, consider a composite bar of two different materials as shown in figure now, which are represented here now, 1 and 2. Let P be the total load on the bar. L1 is representing the length of the first bar, and L2 is representing the length of the second bar. A1 is representing area of the first bar. E1 is representing the Young's modulus of the first bar, and P1 is nothing but the load shared by the first bar. Similarly, A2, E2, P2 representing the corresponding values of bar 2. So, according to the fundamentals, points of composite bars, the total load is equal to, it is equal to P is equal to P1 plus P2, where P1 and P2 are representing the load shared by each bar. P is representing the total load that is acting on the composite bar. Now we are considering stress in the bar 1 now. Sigma 1 is representing the stress, which is equal to P1 divided by A1, and the strain is equal to, that is epsilon is equal to sigma 1 divided by E1, which is equal to sigma 1 is equal to, already we got P1 divided by A1 into E1, it is there P1 E1 now. Okay, this is called strain now. Elongation is equal to, that is equal to delta L1, it is representing the elongation produced in the bar 1, which is equal to the epsilon 1 multiplied by the L1, that is stress multiplied by the length of the bar. Stress is equal to, here now strain multiplied by the length of the bar. Here strain is equal to P1 L1 divided by A1 E1 now. Similarly, elongation produced in the bar 2 is equal to delta L2 is equal to, we can take it as P2 L2 divided by A2 E2 now. Since the elongation produced in each bar is the same now, hence the equation second and third both are treated as equal now. That means delta L1 is equal to delta L2, that is P1 L1 divided by A1 E1 is equal to P2 L2 divided by A2 E2 now. But the length of the bars, that is 1 and 2 both are same now, hence we can cancel these two equations now. So the remaining equation is P1 divided by A1 E1 is equal to P2 divided by A2 E2 now. But P is equal to P1 plus P2, that is load sharing now, which can be written as P1 plus P1 is equal to, we are having in terms of this one is equal to, we are having P1 divided by A1 E1 is equal to P2 divided by A2 E2. So P2 is equal to, we can take it as P1 divided by, here now A1 E1 multiplied by A2 E2 now. So it can be written as now P1, when we are taking common P1, the remaining value is 1 plus A2 E2 divided by A1 E1 now. Or in other words, it can be written as now P1 is equal to, that is P is equal to P1 into A1 E1 plus A2 E2 divided by A1 E1 now. Similarly, by using second equations, we can take it as P is equal to, in terms of P2 into A1 E1 plus A2 E2 divided by A2 E2 now. These two equations are useful for us for determining the load shared by each materials of composite bars now. Since the strain produced in each metal is same, because each metal is producing same elongation or contraction depending on type of the load, hence the strain produced remains constant, which can be written as P1 divided by A1 E1 is equal to P2 divided by A2 E2. In this equation now, we can take it as P1 divided by A1 is equal to, that is stress produced in the bar 1 now, hence P1 by A1 is equal to sigma 1 into E1 is equal to, we can take it as sigma 2 E2 and so on. So from these relations, we can determine what is the stresses that is produced in each bar now. Okay, from the equations, we can find the stresses produced in each bar now. So we are taking one problem based on composite stresses here now. A block shown in figure weighing 35 kilonewtons is supported by 3 wires here now, one aluminum here now, and this is there now, one more, and 2 aluminum and one aluminum and 2 steels as shown in figure now. The outer 2 wires are steel and have an area of 100 mm square each, whereas the middle wire of aluminum has an area of 200 mm square now. If the elastic moduli of steel and aluminum are 200 gigapascal and 80 gigapascal respectively, then calculate the stresses in the aluminum and the steel wires. Since these are the composite structures now, so the strain produced in each bar remains constant, and the total load 35 kN, it is shared by steel as well as the aluminum. Here the given data in the problem is the total load is equal to P is equal to 35 kilonewtons, that is 35 into 10 to the power of 3 newtons. The total area of the steel rod is equal to, we are taking simultaneously the sum of the bar 1 and also the 2 now. It is equal to 2 into 100, because 100 is nothing but representing the area of the steel bar is given. So total area is equal to 2 into 100 is equal to 200 mm square now. The area of the aluminum rod is equal to 200 mm square. The modulus of elasticity of the steel is equal to 200 gigapascal, 200 into 10 to the power of 3 Newton per mm square. Modulus of elasticity of aluminum is equal to 80 into 10 to the power of 3 Newton per mm square. The load is supported by the wires, which is P, capital P is equal to 35 kilonewtons, 35 into 10 to the power of 3 is given now. Sigma S is representing the stresses in the steel wires, and sigma is representing the stresses in the aluminum wire. L is equal to length of the wire now. The increasing in length of the steel wires is equal to delta Ls is equal to, according to these equations, sigma S into L divided by Es now. Where sigma S is representing the stresses in the steel bars, delta L is representing elongation produced in the steel bars, Es is representing the Young's small s. So substitute the values we got to, it is equal to this equation. The increasing length of the aluminum wire is equal to delta A is equal to sigma A into L divided by Ea, which is equal to sigma A into L divided by 80 into 10 to the power of 3 now. These two equations, since the increasing in length in the steel as well as the aluminum both are the same, therefore just we can equate this equation number here 1 as well as the 2 now. That is sigma S into L divided by 200 into 10 to the power of 3 is equal to sigma A into L divided by 80 into 10 to the power of 3 now. So sigma X is equal to here now, L is remains constant, both are same now. I can cancel nothing but here now, 1 0 and 1 0, it get cancelled now. 10 to the power of 3, 10 to the power of 3 also get cancelled now. So sigma S is equal to, I can take it as here now, sigma A, that is here now, 20 it is here now, the 5 into sigma S, because I am cancelling now, 4, 2 ja, 4, 5 now. So sigma s is equal to 5 into sigma s divided by 2 into sigma a. From this relationship 2.5 into sigma s divided by sigma a now. The load supported by 3 Ys is equal to, we can take it as here now 35 into 10 to the power 3, this is the total load, which is equal to sigma s as plus sigma a into a now. Here it is equal to 2.5 sigma a, because sigma s is equal to, we got it now, into 200 plus sigma a into 200, which is equal to 700 sigma a now. Or sigma a is equal to 35 into 10 to the power 3 divided by 700, which is equal to 50 Newton per mm square. It can be written as 50 megapascal. Similarly, sigma s is equal to 2.5 into sigma a. 2.5 into 50 is equal to 125 megapascal. Okay, these are the stresses produced in the aluminum as well as the steel bars now. Okay, principle of superposition now. Till now we have taken all the problems in which the load is acting at the end positions only. This load, it may be in the nature of compressive or it may be in the form of tensile nature now. But here in these problems we are considering the structures in which the load is also acting at various locations within the length also now. So we have to solve the stresses produced in each bar by drawing the free body diagram of each sections just after dividing and calculating the elongation produced in each section. So then the total elongation is equal to sum of the elongation produced in each bar. Okay, this principles which is used to determine the elongation produced in each bar by dividing the length into some number of segments is known as principle of superposition now. That is, when a body is subjected to a number of forces acting on its outer edges as well as at the some other sections along the length of the body. In such cases, the forces are split up and their effects are considered on individual sections after dividing. The resultant deformation of the body is equal to the algebraic sum of the deformations of individual sections. This principle of finding out the resultant of deformation is called the principle of deformation. That is splitting the structures into number of segments and calculating the deformation produced in each bar. The total elongation is equal to the sum of the elongation produced in each bar. This is called the principle of superposition. Okay, the relation is here now by using delta L is equal to P into L divided by AE, which is equal to here now we can take it as 1 by AE into, when number section is there now, we can take it as P1 L1 plus P2 L2 plus P3 L3 and so on, where P1 is representing the forces which are acting in section 1 now, A1, P2 L2 is representing now, L1 is representing the length of the section 1 and P2 L2 and P3 L3 representing corresponding sections in the sections 3 and 2 now. Here, taking one example based on this superposition principle. A steel bar of cross-section area 2000 mm square is loaded as shown in figure. Find the change in length of the bar. Take E is equal to 200 gigapascal. The solution, the cross-section area is equal to 200 mm square. It is assumed it is having uniform cross-section. So, V remains constant. The modulus of velocity is equal to 200 gigapascal. It is equal to 200 into 10 to the power 3 Newton per mm square. The forces here 50 kilonewtons acting at a point A as shown in figure and 20 kilonewtons acting at here at B position and C position 30 kilonewton is there now. That is here now it is acting this direction now. Here if you observe now, the sum of the forces which are acting toward the left hand side is equal to the sum of the forces which are acting toward the right hand side now. When the both are equal, then only we can solve the problem now. Now I am dividing this section into entire section into two segments, two sections. One is representing AB, the second one is representing BC as shown in figure now. Now split the forces in such a way that now here I am taking 20 kilonewton into there and acting at B position now. I am taking 20 here as this. That means the 50 kilonewton is there now. And splitting is nothing but 20 kilometers, because in order to produce these stresses on both sides, the forces should be the same now. Hence, I am taking 20 and 20 now. The remaining 30 load is there now. I am keeping here 30 at A, and remaining 30 here already it is there at C position now. That means here I am considering two sections. So one is representing AB and one more is representing AC now. The total elongation produced because of three forces, 50 kilonewtons, 20 kilonewtons and 30 kilonewtons is obtained as the algebraic sum of elongation produced in AB as well as the AC now. Now, I am considering first part AB. It is now subjected to a load of 20 kilonewtons is given now. The elongation is equal to 1 by A into P1L1 plus P2L2. So, which is equal to 1 by A is equal to constant it is for the entire, it is equal to 200 into 10 to the power of 200, and E is equal to 200 into 10 to the power of 3 it is given into P1L1 20 into 10 to the power of 3 into 300 plus P2L2, P2 is equal to 30 into 10 to the power of 3, and the remaining length is given 300 plus 500 is equal to 800 now. So, it is equal to the 0.75 mm. Okay, second problem based on principle of superposition is a brass bar having cross-sectional area of 500 mm square is subjected to an axial force as shown in figure. Find the total elongation of the bar. Take E is equal to 80 gigapascal. The solution is given. The area of the cross section remains constant, that is the uniform entire its length, which is equal to 500 mm square now. The modulus of velocity is equal to E is equal to 80 gigapascal equal to 80 into kilonewton per mm square now. Okay, the forces 100 kilonewtons here now. It is having sections now. One is the AB, the second one is here we are taken that AC, and third one is CD as shown in figure now. So when I am taking this section AB now, first of all we have to analyze the forces which are acting on the bar now. The sum of the forces which are acting toward the left side is equal to, here one is the 100, one more is 30, that is the 130 kilonewtons. Toward the right side, 80 plus 50, that is again it is equal to 130 kilonewtons. First of all, just identify the forces. If an unknown quantity is there now, based on these equations, that is sum of the forces which are acting toward the left side should be equal to the sum of the forces acting toward the right side. We can determine the unknown forces acting at a given section now. So when I am taking AB now, here the 80 is nothing but we are taking just lowest force that is acting now. So 80, we are taking here 80 now. So that means when I am taking other side also I have to take 80. The remaining values we are having here now is acting 20 now. So again for the AC I am taking now, that is here 20 as well as the 20 now. What is the remaining force is there now here now? 30 it is there now. That is 30 plus here 30. These are nothing but two are having tensile in nature. The third CD is having compressive in nature now. The compressive means the length of the bar is shortens, hence it is treated as a negative values now. So the total elongation produced in the bar is given by the algebraic sum of the elongation produced in AB, AC as well as the CD, which is equal to 1 by AE into P1A1 plus P2A2 plus P3A3 now. So which is equal to 1 by A is equal to area, which is given 500 mm square is given now. E is equal to is given, that is smaller 80 gigapascal is given now, divided by P is given. P is nothing but the force which is acting. It is equal to, first one is 80, it is given now, into A1, that is 500, plus second case now 20 into, that is 1500, afterwards minus of 30 into 1200 as shown in figure now. So the totally on doing these calculations, we got this values is equal to 0.85 mm. Okay, the similar problem is there now again now. A steel rod of ABCD 4.5 meters long and 25 mm in diameter is subjected to the three forces as shown in figure now. The value of Young's modulus for the steel is 200 gigapascal. Determine its deformations. Okay, diameter is given. It is equal to, here diameter is given 25 mm. It is given, and Young's modulus is equal to 200 gigapascal, which is equal to 200 kilonewton per mm square is given, or 200 into 10 to the power of 3 Newton per mm square now. The cross-sectional area of the rod is equal to pi d square by 4, which is equal to 491 mm square now. The forces here is given now, total. It is nothing but AB, BC and CD is given now. The sum of the forces which are acting toward the right and left hand side is equal to 60 plus 10 now, it is equal to 70. Toward the right side now, 50 plus 20, again it is 70. Hence, it is possible to us to solve the problems. Okay, in this case now, we are taking now, first AD we are taking, it is equal to 50 now, other side is also 50, it is there. The second one is given now, 10 now, it is given at C position now, again 10 position we given, and BC we are taken now, it is nothing but 10 and 10 now. So, we can take the cross section in such a way that now, that the total amount of force toward the left side should be equal to the towards right side, that it should be in equilibrium position, otherwise the elongation is not produced now. So the total elongation produced in the bar is given by delta L is equal to 1 by A into P1 L1 plus P2 L2 plus P3 L3. So and substituting the values of here A is equal to 491 now, E is equal to 200, it is given now, into P1 is equal to 50 into, here L1 is equal to 4.5 into 10 to the power of 3 given, plus the second one is given, P2 is equal to 10 now, L2 is equal to 3 into 10 to the power of 3 because we have taken here 3 now, plus 10 into 1 into 10 to the power of 3 now. So on simplifications we got this value is equal to 2.70 mm now. Okay, by using these principles we can determine the elongation produced in each bar, and this principle is called superposition principle.
Like, share and subscribe. Hit the bell icon for more updates.